I love speaking here so much that I just love this community, and especially coming from academia, I love how this world is so non-hierarchical. I actually work on hierarchical models, but I feel kind of bad about, so we call them multi-level models. There's no levels are higher than other levels. And like, it's not about credentials or even like about money, like in this world. Like, it's just like people doing the work, and I just love that. So my favorite place to speak ever, except for the STAN conference, of course. Now, when I spoke at the STAN conference, I prepared my talk. It was called 10 Things I Hate About STAN. And my STAN, co-STAN people were like, you can't do that. Like, it's like, no, it'll be fine. And so it was okay. So then I was going to speak here. So Jared said, what talk about? I said, well, let's do 10 Things I Hate About R. Or actually, like, you guys, it's a big conference, 20 things I hate about R. And Jared was like, you can't do that. I said, well, what do you mean? He said, well, you don't understand. The STAN, it's like a close-knit community. The R people, like, well, to be honest, they don't all have such a great sense of humor. Like, so Jared was like, if you say something negative about R, they'll jump down your throat. It's like a VI Emacs kind of situation with these people. So I had to throw away my slides. That's why that's blank. So I want to sort of like cast a critical eye on statistics a little bit. R is great. We all know that. How do we know this? How do we know it? I think I've solved a lot of problems with R. Sometimes I'm stuck. I can't use another tool. I use R. Other people find it useful. I've heard that it's increasingly searched for on Stack Overflow. I feel like we got to get more Stan questions in there now, so I can be on the next slide for that. I kept looking for Stan, but we're in the we have our own group, of course. But if you were to like take an introductory statistics textbook or class, you say, well, how do we know something works? That's not supposed to be good enough. Like, I use it, so it's good, right? So statistics textbooks and intro stat classes are full of stories where people, like, they think the treatment is great, but actually it's not, right? Like, they think this treatment hurts, but actually sick people take the pill and healthy people don't. And when you do a controlled experiment, you find it really works or it doesn't work. Lots of examples of surveys like, they did this survey, but it wasn't a random sample, and so they were wrong, et cetera, et cetera. But when statisticians talk about what they do, like what tools do they use, or I don't know, why is Bayesian inference a good thing? Did you do a controlled experiment, like comparing Bayesian inference to something else? Like, no, we didn't do that. Or like, people love my class. How do you know? Well, did you do a survey with it? Well, no, I didn't actually do that. I did the equivalent of the Literary Digest poll, like conducted underwater or something, or did like nothing. Oh, how do I know that my class is effective? Well, of course, I did pre-test and post-test, and I did a controlled, well, no, I didn't do that controlled experiment of 2 different ways of teaching my class. But that's okay because I didn't have a pretest. So with that, you need that pretest because even with a controlled experiment, you have people dropping out, doing different things. You need to control for that. So it's too bad I didn't have a pretest, but that's actually okay because I don't have a post-test either. So I have no measure of my outcome. Oh, but that's okay because I don't actually know what my treatment was. I didn't even record that. So like, you see the textbooks, it's like, oh, you better randomize. Randomization's like number 15 on the list of things you should do. First, you should figure out what your treatment is. And then you might want to think about like what your measure of success is and your pretest measurement and so forth and so on. There's so much. So we're not doing any of that. And I'm not sure what that means. Maybe it means that we should be doing that sort of thing. Maybe we should be evaluating the use of R experimentally. Maybe it means that these principles don't really apply. Maybe we're teaching a bunch of useless stuff. Maybe the principles apply, but only in other problems, not in anything that we directly care about. I'm not sure. sometimes we can shift what problem we study. So there's this whole story about decision analysis. In the textbooks, decision analysis is typically described in terms of personal decisions. And they'll give these little vignettes, right? Like your nephew is trying to decide where to live. And he could live off campus, which is less convenient, but it's cheaper. He could live on campus. And they balance the things, and there's a value function. But nobody solves their decision problems this way. You wouldn't really recommend it. There's a sort of garbage in, garbage out aspect to that. Like, it's more like you figure out your decision, and then you can go explain it. Does that mean decision analysis is useless? No. I have the term institutional decision analysis. That if you're an institution, like a company or division of a company, a division of a university, you have to make a decision about how to invest your resources, you need a paper trail. You should have a decision analysis. You should have to defend it. This comes up a lot. I've been known to recommend that when people analyze noisy data, that they use prior information. And some people have said that they don't really have the prior information. That's why they're doing the damn experiment in the first place. And what I say back to them is, I would like you to state what your assumptions are. And if you can go from there. And you should have to record what your assumptions are that drive your conclusion. So for example, there is a study, I might have mentioned it one of my previous talks here. There's a study a couple years ago of early childhood intervention where they did an experiment on some kids, 4-year-old kids in Jamaica, and some of them got an intervention and some didn't. They followed them up, and the kids, 20 years later, the group who had the intervention was making 40% more money than the group that wasn't. And the difference was statistically significant. It was like an estimate of 40% with a standard error of 15%, or something like that. That's kind of, so these estimate is a very reasonable estimate if your prior distribution on the effect size is anywhere from -infinity to infinity, a nice uniform distribution, or even something like uniform between 0 and an 80% improvement would give it to you. I would like the researchers to have to write that down. If they want to publish that their point estimate is 40% improvement, I want them to have to say in section 3.2 of their paper, we assumed a prior distribution that was uniform from 0 to 80% improvement. And then I could say, well, geez, I don't really think that helping out a 4-year-old's mother for a year is going to give them an 80% improvement in their income when they grow up. I find that hard to believe. I don't see the evidence there for that. And they would have to defend it. So I think it's actually important to do. So to sort of reel this back in, decision analysis, I like the idea of institutional decision analysis. The concept is still valuable. Similarly, I think a lot of the concepts of designed experimentation and random sampling are useful, even though they don't always describe what we do. I think that one thing, well, let's talk about the Hadley verse for a second. Okay, so it's not only that we have to live in the Hadley verse whether we want to or not, okay? The real issue with the Hadley verse is that we want to live in the Hadley verse. This is where we want to be. This is where you want to be hanging out. Now, what's so special about this universe, this tidyverse, where we would like to live? To me, what's super special about it is that the Hadley verse is larger than our usual solar system or our usual galaxy. Okay? The Hadley verse includes things which traditionally were not even quite considered part of statistics. They were just considered good practice. Now, I want you to, I think of the history of statistics to a large extent being folding things in that seem like good practice, formalizing them, and turning them in, and routinizing them, turning them sort of into mathematics. So just step back a little bit and let's talk about the weather. It's a popular topic of conversation. It's kind of moved, our thinking about the weather over the centuries has moved from, you might say, from religion to philosophy to science to technology. So the thunder used to be the gods throwing down thunder because they were angry, I guess, or maybe because they were just in a good mood. Then there was a philosophy like, what does the weather mean? Where is the weather coming from? It's from some imbalance in the humors of the earth, whatever those scholastics used to say. Then to a study of science, and as I said, now something that you can measure, and it's studied technologically. Now, similarly in statistics, go back 150 years in statistics. People were not doing random sampling. Of course, you kind of know, I'm sure that the proto-data scientists of the era knew that you wanted a representative sample, but it was like, that's like good practice. Like, oh, your sample's supposed to be representative. Or they weren't doing randomized experiments. Of course, when people did experiments, they would try to balance, what would it be like if all else held equal. But it's kind of like, oh yeah, you're kind of supposed to. Just like in the old days before the Hadley verse, like, oh yeah, tidy data, you're supposed to, like, that's good practice. So the role, in the sense, the role of academics like myself, I see sometimes as trying to take practice and put it into our general theory. That's why I was talking about theoretical statistics as the theory of applied statistics. We can think of really a lot of examples of that in hierarchical modeling. So in the old days, let's say as recently as 40 years ago, you would see discussions in statistics journals about multi-level models, hierarchical Bayes, empirical Bayes, whatever they would call it. And it was treated almost as a subject of philosophy. So there's this kind of paradox. It goes like this. Suppose you have data from 8 different groups, and you want to partially pool your inferences because your inference from any different group is sort of noisy. So we know now you can fit a hierarchical model. It's very straightforward. When people were developing this technology back in the 60s, 50s, 60s, and 70s, there would be objections, and people would say this. They'd say, how do you know whether it's appropriate to partially pool information from different sources? So there'd be these examples, like someone might publish a paper where they have information from 8 schools, and they'd put them together and get better inferences. And then somebody else would say, well, what if we have data from 7 schools and something unrelated, a measurement of the speed of light? Okay? Well, you shouldn't pull those together, but where in the math does it say not to do that, right? It's just like the math says if you have j equals 8, you can do that. So it was this sort of weird thing, like, are the situations exchangeable or not? It was this awkward thing. As our understanding grew, we realized that this is actually sort of a mathematical question or a technological question. So for one thing, if you have 8 schools and 7 schools and the speed of light, they're going to have a very large variance, which means you're going to do very little partial pooling. You'd actually be better with a mixture model. So it's a distributional question. You have 8 things, and they're not coming from a normal distribution. They're coming from a distribution that's a mixture of 7 and 1 and 1 of the other. If you fit that, you'll kind of get the right answer. Or you actually have information, of subject matter information, that the speed of light is different from a school, then you can put that in too. But the point is that it all does fit into the mathematics. Another example would be regularization. So we know about lasso or Bayesian methods, all sorts of methods will fit your data automatically. Well, back 40, 50 years ago, people would talk about that, and they'd say, how much should you regularize? It was this tuning parameter. Now, we have all sorts of ways of estimating the tuning parameter. We don't think about it. But it used to be considered like almost like a personal preference. Like, I like it smooth, I like it rough, like that kind of thing. What's another one? Model checking. So back in 1991, I went to a Bayesian conference just full of Bayesians. And that's all they were. And I was going up, like, looking at the talks, the posters. People would fit these models, and I'd be like, does your model fit the data? Like, could I see, like, I remember one case in particular, someone's poster, and it was a model of the circadian rhythms, when you sleep. And there were, I think, circadian rhythms is not when you sleep. It was the model of sleep. And I think they had, people had like 4 stages of sleep, and they were doing something where they're measuring people in the middle of the night. I don't remember the details, but you have this time series jumping up and down. They had a statistical model, and they fit it. And I was thinking, hey, could you create some simulated replicated data from your model? Like, why should you do that? Well, I just want to see if your model fits the data. Like, no, you don't understand. Like, we can't check whether the model fits the data. You're not allowed to do that. I said, why not? Well, because our models are subjective, so they're uncheckable. So, well, I guess that makes sense, because they're subjective. You shouldn't want to check them. Why are you telling me your model? Why are you talking to me at all, right? I mean, just go back into your cave, you know? But the issue was that their philosophical, their theoretical framework was too narrow. So they were somehow here. And so over the years, we've incorporated model checking into Bayesian data analysis. So now, like, you could say, well, you don't have to feel bad about model checking if you're a Bayesian, but it's actually more than that we can check our models more effectively. So it's kind of funny when you look at a book like Tukey's Exploratory Data Analysis from 1977, or his paper from 1970 that it was based on, he had a lot about graphics, but nothing about models. Tukey was an old-time modeler. He invented the fast Fourier transform, but he didn't like the models. He was using the sort of kick the ladder out from under us approach to statistics, which is you can use the models to create these graphical ideas, and then you should just look at graphs, not do any models. But what we've learned since then is that if our models are more advanced, we can actually do more effective graphics. And so that's another example. Another example would be missing data. So traditionally, it's like missing data is like a pain in the ass, right? It's like, oh, I'm missing data. Let's do something about that. But maybe we should model the missing data process that you can do better than that. And that's, in the 70s and the 80s and 90s, a lot of work was done in that area. Also in particular applications. Survey non-response. I still deal with people who do work in the survey sampling industry who don't like to think about survey non-response. It's, a good survey might have, a good telephone survey might have a 9% response rate. So those of you who are sort of good at math in your head will realize that that's a 91% non-response rate. It's kind of an issue. So we can handle that. So like when we do Mr. P, the non-response is right there. It really makes a difference in real surveys. So I don't know if any of you saw, there was an article in early October in the New York Times about where they did a survey in Florida, and they sent the data to 4 different pollsters and had them estimate the polls, the standing of Trump and Clinton in the election. And different adjustment methods gave different results. But the group that used MRP happened to say that Trump was ahead by 1 percentage point. That's just one case, of course. But the point is that the idea of taking something that was considered outside the realm of statistics and putting it into statistics, I think is incredibly valuable. It's maybe hard for you to believe, but if you go back to the old literature, missing data was not really treated in a systematic way. It was considered something to look away from and not think about. And we'll still see this in a lot of experimental sciences. Like in medicine, biology, psychology, you see published papers, and the missing data are wished away. You just have the table, and people get dropped out, and they don't even tell you why they're not there. Because they don't have a way of handling it. Right? They don't have a way of talking about it. They know they're not supposed to. So I think the Hadley verse, I love it, well, just for what it is, but also as an exemplar of this idea that we can think and act systematically about things that were considered to be merely sort of matters of grooming, as it were. So I want to talk a little bit about workflow. I think workflow is very important to all of us. I think this is a room of people who do work, who analyze data. I would like for our workflow to be more formalized. So I would like the same way that Partial pooling got integrated into Bayesian hierarchical modeling, the same way that model checking became formalized, or missing data analysis. Similarly, I think there are many steps in our workflow which now are considered good workflow, but yet are not formalized. And I would like us to be able to do that. So, of course, as I said, some of this that we've done, like model checking, so we have a sort of proto-workflow. And the proto-workflow is you build a model. You build a model, you do inference, you check the model using predictive simulation, then you improve the model. Now, that's not new. I mean, that's in page 1 of first edition of Bayesian data analysis, 1995. So it's not, that part is not new, but it's missing a bunch of steps. So some of the steps are conceptually not such a challenge, like being able to fit bigger models, scalability. What I spend most of my time doing is scalable inference. But the model checking part, there are some open questions like what graphs are you supposed to look at? Often it helps to fix the mind to think of an artificial intelligence trying to solve the problem. Like, so I somehow imagine an AI that's doing Bayesian data analysis and fits a model and then decides it wants to check the model. So what it does is it goes into R and it writes a program and makes a graph. It prints out the graph. Then it has like a giant robot arm that carries the graph onto like a scanner. It scans the graph in, and then it puts it into sort of a robot retina, which then reads it and then looks for patterns, which is kind of ridiculous, except that's what we do, right? So it's not so ridiculous, but maybe there's a more efficient way of doing it. At least you don't have to print it out. Right? Color printers always running out of ink and all that. So part of it is how do we systematize that? The idea of model expansion, model building, so that's always mysterious, right? So in statistics, a statistics textbook, I'm really standing here, so move around. In a statistics textbook, it's like, how does it work? Well, there's this experiment that gets done. Like I have a treatment. Right, so how does some smart scientist, that can't work. Some smart scientist comes up with a treatment, and it's compared to the control, and then they do a randomized experiment, and then it's statistically significantly better, and so lives are saved. End of chapter 4, right? That's how it goes. Well, sort of like where did that scientist come up with the idea? Well, maybe using some other statistics that's not there. There's a problem, though. I wrote a paper recently called Null Hypothesis Significance Testing is Incompatible with Incrementalism, which was my personal attempt at like the worst possible title of, like, I had this idea that if the title is that bad, it's good. Like, it's so, so you're like, null hypothesis significance testing is incompatible with incrementalism. What does that mean? It's like, it's actually good. Like those graphs that are so hard to read that people like them because you have to like figure them out, right? And so, but my point was that in a lot of the world, like our treatment effects are incremental. So in medicine, it's kind of required that your treatment effects be incremental because you're supposed to compare the treatment with the best available alternative. Not like, okay, we're either going to do this great drug or a sugar pill. No, it's supposed to be the great drug versus the current status quo. It's probably an small incremental improvement. But when the treatment effects are small, then you're going to have your standard error is going to be big compared to your estimated treatment effect. The statistical significance filter says your estimates are going to be too large. This is what happened with that study in Jamaica of the early childhood intervention. These effects are small, but the data are very noisy. And of course, with something like early childhood intervention, you can't do a within subject design. It's very noisy, so the effects are going to be overestimated. While overestimating the effect size, maybe that's good because early childhood intervention is a good thing. Maybe we should be overestimating the effect sizes. But then I think we should be honest about it. But it's a funny thing because that estimate of 40% that I told you about, and I'm picking on this study not because it's bad, because it's good. Right? It would be easy. Picking on a bad study is easy. I don't do that sort of thing. I don't talk about bad research. It's boring. Right? What I want to talk about is the good stuff. Top researchers doing a serious study. But it's a hard problem. Right? So how are we going to deal with that? How are we going to study this? It's an unbiased estimate, right? They're taking the mean. Forget about missing data and stuff like that. They're running a regression, whatever. They have a coefficient. It's not an unbiased estimate because remember the theory of theoretical statistics is the theory of applied statistics. You have to study what we actually do. So if the standard error is 15%, then the estimate has to be at least 30%. It's either plus 30 or higher or minus 30 or higher. So the absolute value of suppose the true effect size is, say, 3%, then the estimate is guaranteed to be 10 times bigger than the truth. That's kind of horrible. It's not unbiased at all. It's really, 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 really biased. It's biased by a whole order of magnitude. Okay, now anywhere outside of astronomy, an order of magnitude really means something, right? So yeah, that's too bad. Well, so what do we have? We have a bunch of p-values that don't actually represent the probability of seeing something more extreme than what you observe if the null hypothesis were true. And you also have a bunch of confidence intervals that are actually not correct 95% of the time. We have a bunch of unbiased estimates, supposedly unbiased estimates, which on average are biased. They're too large. Okay. So obviously our theory has some gaps. Our theories have some gaps, but my Bayesian approaches have some gaps too. As I said, where do the models come from? So I have an idea. So the idea, this is not a unique idea to me. The idea is that there's model space. So you're perhaps used to, some of you are used to thinking of graphical models, of thinking of variables in a space connected by nodes. But this is not what I'm going to talk about now. I'm going to talk about a space of models so that it's a space in which each model is a node and they're connected by edges. So I have a model which is like, I take the average, I can take the difference between the treatment mean minus the control mean. And then I have something where I control for pretest, so that's connected. Then I have another thing where I control for groups, and I have a multi-level model for that. That's another model. Or I could have the groups and the pretest. Or I could have the groups interactive with the pretest. Or I could have a measurement error model, because the pretest is measured with error. Or the treatment could be measured with error. I could have a dropout. Every time I add another twist, it's like I'm connecting it to the model. I'm putting it together. So model building it's like language. I mean, it really is. Like Stan is a language. Like what that means is that there's not a menu of models. It's not like there are 8 models we can fit. Okay? Just like when we speak, we're not like one of those characters like from the totalitarian government who can only speak one of 18 sentences, and each time he talks to you, he uses one of the sentences, and you have to figure out what he means by the context. It's not like that. Okay? What it's like modeling is like I'm speaking here. I'm saying a sentence that's never been said before, amazingly enough, even though I'm putting together just a bunch of simple words. Right? We put it together. So model building. Right? Modeling model building requires a sort of calculus of models. It requires this idea that models are connected to each other. Now, I think that's a bunch of talk. We need the computer program that does it too. Like computer programming is basically the last bastion of rigor in the modern world. And I don't trust anything until it runs, in fact, until it runs twice on the computer. It's funny, I'll tell you a story. When I was in college, I took a class, it was called Introduction to Design, where we had to build a machine. There's a beginning part of the class which was kind of boring, but at the end I basically spent 2 weeks without end in the machine shop, except like it was only open 14 hours a day. So I would get in there at 8 in the morning and go until 10. And we're building our little machines. And one thing, there's a couple things you learn. One is that the laws of physics are immutable. And you try to build like a trigger, and if you don't have a long enough lever arm, it's just not going to trigger, things like that. But also, something can work 5 times and then break, which is kind of funny because when you write a computer program, if it runs, it runs. Well, maybe not anymore, because if you write for somebody else, the environment can change. But in some sense, like a machine, really, like if you put too much stress, it will break. And so that's another world entirely. So I would like you all to remember that you spend most of your time on the computer, but the real world physical world has other aspects to it. So I think we need a theory of models. Now, this connects to model building. So if you had an AI building a model, the idea is it would sort of walk along these. Just as if you wanted an AI to speak, it wouldn't choose sentences out of a basket of sentences. It would try to imitate how we form our sentences, how we have our thoughts. Then in model checking, similarly, there must be a way to do this. One thing that I find is a challenge, is an open question about this network of models is how do you relate them to each other? Because I don't want to just say, here's a model, here's a model, here's a model, and like I'm going to compare them based on which has minimum wake or which has minimum cross-validated error or LU or whatever. That's not really the point. And I can say this in two ways. One, there's just a lot of models out there. There's more models than you could possibly compare that way. Another way of saying it is that suppose that I knew the correct model. I mean, either the true data generating process or like the model that I ultimately want. I know that I want it. Even then, I would like other models. I would like a model that's simpler, that's a little simpler because to show that the model without this feature wouldn't work, right? So I need a model too simple that shows why I need to do what I did, and then I need a model that's a little more complicated to show that yeah, I could have added more to the model, but it wouldn't have changed anything. So at the very least, I need to know that. Well, how do I compare models? I don't want to just compare their LU, their leave one out, error, anything like that. I think usually when we compare models, we compare them at the parameter level. So there's this way that you have models in model space that are connected by nodes when they're similar to each other, but then there's an operation which is to compare models, and then you're connecting, like if the model itself is like a little graph, you're comparing the parameters of the model to each other. So this is complicated. So we need a theory for that, right? So like, again, like this is not, the Hadley verse is not going to solve this particular problem, but I mean, that's fine, right? Like I haven't solved it either. But the point is that the Hadley verse is to being clean with your data as this hypothetical, non-existent R package or whatever it's called theory for model integration is to this problem of comparing models, building models. There's a lot that we do that we don't have theory for. So what is theory? I mean, does theory have any value at all? Does math have any value at all? I mean, a little math is good, right? Like, for example, hey, I have my problem, and I fit it on 1,000 data points, and it took 2 minutes. What if I had 10,000 data points? Would it take 20 minutes, 200 minutes? Well, it depends how it scales. Obviously, a little math is going to be helpful here. I can give you another example. A few years ago, my colleague and I were forecasting a presidential election. It was 1992, actually. We weren't really interested in forecasting the election. We were interested in demonstrating the election could be forecast using fundamentals, not using polls, but just using economic conditions. So we did this state-by-state forecast. And as a byproduct, we computed things like what's the probability the election is exactly tied. So it goes into the House of Representatives. What's the probability that your vote is decisive so that the vote in your state is tied and your state is required for the national vote for the Electoral College for your state to matter? So to do that, like we used there had been a literature on this which was purely theory-based, like binomial distribution. It's ridiculous stuff. There's somewhere I saw someone, there was some paper and it said the probability of the election being tied is 1 in 10 to the 92. And that's, I mean, well, of course that's ridiculous because the election's sometimes within 1,000 votes, right? So like it somehow can't be much less than like 1 in a million or 1 in 10 to the 92. It's just the wrong order of things. It's enumerate. But that was a pure theory approach. You can do a pure empirical approach where we have a forecasting, you do simulations, but you would need to do like 1 billion simulations in order to figure out like what's the probability it's tied. So we used a little theory. You can figure out the probability it's within 1,000 votes and then divide that by 1,000 and there's some smoothness. So that worked. So this gives me some insight. What is theory? What does theory give for us? Theory is scalable, right? Simulations are not scalable, but theory is scalable. And that's what it gets us. That's the theory of theory. But it's not always presented that way in the textbook. So why do you need to learn the central limit theorem or whatever? You'll need to learn it because it's scalable and you can't figure out what's going to happen. So hopefully, with a small sample, you do the simulation, and with the large sample, the theory will work. Of course, you need theory of the approximation and so forth. There's a lot of room for meta theory also. This came up recently. We had a discussion in the blog about whether programming should be a prerequisite to learning statistics. And I think some people correctly said, no, it shouldn't be a prerequisite. Really, like, programming is kind of hard and statistics is kind of easy. And so, like, you shouldn't, like, for example, you should be able, like, the graphs that were made in the previous talk were made using a lot of programming. However, if someone wants to be a statistician or to use statistics, he or she should be able to learn how to make graphs like that without having to program, like using a menu or whatever. Certainly, we should be able to interpret such graphs without programming. So there I agree. But there's a saying, so in the 20th century, I'm still not completely used to saying that, like in the past and that. But in the 20th century, it was said that if you wanted to be a statistician, you had to be a little bit of a mathematician, whether you wanted to be or not. So I think maybe you can see where this is going, that in the 21st century, if you want to be a statistician, you have to be a bit of a programmer, whether you want to or not. So programming should not be required prerequisite. You should be able to take introductory statistics and sort of get your way through it. But it should certainly be it should be no less of a prerequisite than mathematics. I think that if you want to make the argument that you can do statistics without any programming at all, I will believe that. I accept that argument. If you now want to make the argument that you should be able to do a certain amount of statistics without any math, like not even algebra, forget about calculus, but not knowing how to solve for x, then I would say yes, you could. Of course, it'll help if you know how to program. Now, you'll be a better programmer. You'll be a better statistician if you know how to program and if you know how to do a little math, and you can like solve algebraic equations for x. If you don't know any math, it's going to be hard to understand these 1 over square root of n things. But if you can program, you can get at it another way. Programming is more important than math, I think. So it's getting, but we have to sort of get used to understanding that. So I would just like to conclude by saying that workflow is such an important part of our work lives. I mean, each of you must, I can't imagine anyone would disagree with me when you say that not only do you spend a lot of time sort of on your workflow, but I think each of us spends a lot of time thinking about our workflow. Like you actually spend a lot of time analyzing yourself, thinking what will work, what doesn't work. And workflow is an app to the extent that we do statistics, as I'm sure some of us do, or data science in this room. Much of workflow is still not inside the tent of statistical theory. And I think it could be. I think we should be heading that way. And I think in the meantime, we should be thankful for how much current statistical theory methods does include. We should be thankful for the Hadley verse. We should be thankful for languages such as STAN that incorporate model building as part of the process. And I think we should all, each of us, when we are doing our work, we should look at what we're doing and we should think about our workflow in an abstract way. We should think about there's a principle in programming that you should never type the same line of code twice, right? And similarly, like if you're doing something over and over, you try to systematize it. Try to systematize your systematizing. Try to think about what you're doing and create principles. Be an amateur statistical theorist because we, the statistical theorists, haven't caught up to you yet. And I think you can do a lot. Just as if you imagine like someone doing a sample survey in the era before random sampling could come up with a lot of good ideas by recognizing the challenges that they face. So you should do that. You should respect your own challenges and try to come up with a theory of yourself rather than waiting for us to do it for you.